So we're now ready to see how Maxwell's equations, and what I have here are the important parts of Maxwell's equations in vacuum. So this is Faraday's law, and this is Ampere-Maxwell, except I've gotten rid of the Ampere part of Ampere-Maxwell because we're in vacuum. There are no currents, so the only term on the right-hand side of Ampere-Maxwell is this one. So these are the two important parts of Maxwell's. These are the two important Maxwell's equations when we're talking about solutions in vacuum. And I want to start now walking you through how these equations have solutions that look like what's depicted in this diagram. So before we start, let's remind ourselves what this diagram shows. This diagram shows EY, okay, EY are the yellow, it's a graph of EY, the yellow arrows, and BZ, the blue arrows. It's a graph of EY and BZ as functions of x at one moment in time. So this is a snapshot of the solution at one moment in time, showing how EY and BZ depend on x. So the way I'm going to begin is I am going to apply this equation, Ampere-Maxwell, to the red rectangle in this diagram. Why? Why am I picking this red rectangle? Well, at this second, it's just because I said so. Okay, we'll see as we go along why I made the choice of this particular red rectangle. For this moment, trust me, and let's try applying this equation to the red rectangle in the diagram. So this red rectangle, I'm going to redraw it here. I'm going to draw it divorced from its context. So here's a red rectangle, this red rectangle from this diagram. And I'm going to choose to do my contour integral of b dot ds. So I'm going to start evaluating the left-hand side of this equation, the contour integral of b dot ds around this contour, and I'm going to choose to go around the contour in this direction. Now, you can see that the way I chose the orientation of this red rectangle, if you look at the diagram, I chose the orientation of the red rectangle so that the long side of the rectangle is in the b direction. I did that because I wanted to pick up a non-trivial integral of b dot ds. If I had chosen the red rectangle to lie in the perpendicular direction, then the long sides of the red rectangle would have been perpendicular to the b's, and I wouldn't have gotten any significant contribution here. So the reason that I chose the red rectangle oriented in the way that I did was so that I could analyze a non-trivial contour integral of b dot ds. So let's start working this out. So let's first of all dispense with the two short sides. So these short sides go in the x direction. And remember that in our solution that we're looking to analyze, there is no bx. There's only a bz. There's an ey and a bz. There's no b in the x direction. So that means integral of b dot ds along these short sides is just 0. We'll forget about them from now on. So integral of b dot ds is going to come from the long sides. And if I go too fast, I'll argue as follows. This will be a mistake, as you'll see. But if I go too fast, I'll say, well, OK, these long sides are L in length, let's say. And so I'm going to pick, and if I look in the diagram, I see that the b is pointing this way. So I'm going to pick up a minus BL along this axis and a plus BL along that axis, and they're going to cancel. So if I do this analysis too quickly in a sloppy way like that, I reach the wrong conclusion. I think everything vanishes. This is 0. That's not correct, and the diagram shows you why it's not correct. The fancy diagram over here shows you why that's not correct. It's not correct because the value of b is not exactly the same at this x as at that x. So let's call this separation here delta x, as in the diagram. And the b at x and the b at x plus delta x are in fact not the same in value. And that is why when we evaluate this, we don't just get 0. What do we get? Well, what we get is from this side, okay, from this side of the loop, we get bz. If evaluated at position x and time t. The time t is the moment at which we've taken this snapshot, or at which we're doing the analysis. The entire analysis is going to be at one moment in time, which I'm calling t. So I get bz times L. Now when I go up this way, b is running against the contour. I'm integrating along the contour this way, but b is pointing against me, so I have a minus sign. And then I have bz, but now I'm not at the position x anymore. I'm at the position x plus delta x, t. And this also is multiplied by L. So yes, I get bz times L minus bz times L, but the bz here and the bz there are different because they're at different positions. So that's what I get from the left-hand side of this equation. Now I want to start evaluating the right-hand side, and I'll do so in green instead of orange. And so what's on the right-hand side? On the right-hand side, I have mu naught epsilon naught d by dt of E dot n hat dA. What's that equal to? Well, okay, so there's this combination of constants, mu naught times epsilon. Those are just fundamental constants of nature. Then I have d by dt. And what do I have the d by dt of? Well, if you look at the diagram, if you look at the diagram over here, you see that the yellow arrows are coming up through the red rectangle. So there is, in fact, an electric flux through the rectangle. And when I represent that up here in this diagram, that means that there is an electric field. And if you look at the orientation of the electric field in this diagram, and you look at the direction in which I'm doing the contour integral, what you see is that the electric field in this diagram is pointing out of the board, pointing at you. So now I need to do the integral of E dot n hat dA. Which direction does n hat point? Well, if you look at the direction in which I'm doing the contour integral, and you use your right hand, your right hand, okay, n hat points out of the board at you. So E dot n hat is positive. And so what I get here is E. Which component of E? Well, it's the one that's non-zero. It's EY. Evaluated where? Well, I'm going to evaluate it right in the middle of the rectangle, which is at x plus delta x over 2. Evaluated when? Well, the entire calculation is at the time t. And then I need the area of the rectangle, and the area of the rectangle is delta x times L. So there, I've just evaluated the left and right sides of this equation of Ampere-Maxwell, and now we can equate them. So Ampere-Maxwell tells me that this is equal to this. So let's see what we get. And you can see that this is going to become a derivative. So let's keep that in mind. The other thing you can immediately see is that the L's all cancel. So there's an L there, there's an L there, there's an L there. I'm going to set this equal to this. The L's are all going to cancel. I'm not even going to write them anymore. So let's start writing out what we get. I have Bz at x and t minus Bz a little bit over at x plus delta x and time t. The L's have canceled. I'm not writing them. And then I say, aha, there's a delta x here. Because I like the idea of this turning into a derivative, instead of putting the delta x on the right-hand side upstairs, I'm going to put the delta x on the left-hand side downstairs. And now this is a derivative. So what do I have left on the right-hand side? Well, I have this mu naught epsilon naught. And then I have a d by dt. And then I have, remember, my delta x has gone downstairs over here. My L has canceled. And I have EY evaluated at the midpoint. And so what we conclude from this is that if I want to have a solution that looks like this, with an EY and a BZ, if there exists such a solution, if there exists a solution with an EY and a BZ that are functions of x and time that describe planes as I've described at the beginning, if there is such a solution, if it satisfies Ampere-Maxwell, then there has to be a relation between the BZ and the EY, and that relation can be written very simply as follows. So this is, it's dBz dx, except there's a minus sign because the derivative would be this minus this. And since what I actually got was this minus this, that's minus the derivative. So what I have is minus d by dx bz is equal to mu naught epsilon naught d by dt of EY. A nice, simple conclusion. So Ampere-Maxwell, for a solution like this, takes this form. So what's this telling us? This is telling us that, so remember, BZ and EY are both functions of x and time. So I'm taking partial derivatives. This one I'm differentiating with respect to x. This one I'm differentiating with respect to t. And there's a relation between those two partial derivatives. But now let's think about what this is telling us physically. What this says is that if BZ is varying in position, and now let's look at the picture, and you see that BZ is very definitely varying in position. If BZ is varying with position with x, then this side is not 0. That means this side is not 0, and that means that EY has to be varying with time. So we conclude from this that if BZ is varying as I've drawn, then this entire solution, it can't all be standing still. EY has to be changing with time. Something has to be changing with time. So this is our first hint that if we want to satisfy Maxwell's equations with a solution like this, the solution can't be standing still. And what we're going to see is that the solution, in fact, is moving in the x direction. And it has to be moving with some speed, and somehow in these equations have to be telling us how fast it's moving. And that's what we're going to get to in the next couple of videos.